welcome to this problem walkthrough. Today, we'll be exploring problem number 200, number of islands. This is a classic graph traversal problem that tests your understanding of depth-first search and breadth-first search algorithms. Let's dive into the problem and uncover the best approaches to solve it. In this problem, you're given a grid of size m by n, where each cell is either 1, representing land, or 0, representing water. The grid essentially represents a map, and your goal is to find out how many distinct islands exist in this map. An island is defined as a group of ones that are connected in a four-directional manner. This means connections can only occur horizontally or vertically, not diagonally. It's also important to note that the edges of the grid are always surrounded by water. The input will be a 2D list of integers representing the grid, and the output will be a single integer, which is the total count of islands present in the grid. For example, take this grid as input. Here, the grid contains a block of ones at the top left corner, with all these ones being connected either horizontally or vertically. The rest of the grid is filled with zeros, representing water. Since there is only one connected group of ones, the output for this grid is 1. This example demonstrates the simplest case where the entire landmass forms just one island. Now, consider another example. In this grid, we can see three separate groups of ones. The top left corner has a 2 by 2 block of ones, which forms the first island. There's a single one in the middle at position 2, 2, which is not connected to any other land, so it forms its own island. Finally, in the bottom right corner, there are two horizontally connected ones, which together make the third island. Since there are three distinct islands in total, the output for this grid is 3. Finally, let's look at a case where the grid contains no land at all. Every cell in this grid is 0, meaning it is entirely water. Since there are no ones, there are no islands in the grid, so the output is 0. Keep in mind several constraints for this problem. The grid dimensions can go up to 300 by 300, and every cell is either 0 or 1. Some important edge cases to consider include grids with all water, grids with all land forming one large island, and grids with multiple islands of varying shapes and sizes. Remember, diagonal connections don't count, which can sometimes impact how islands are identified. When tackling the number of islands problem, we can start by considering the brute force approach. The intuition here is to systematically visit every cell in the grid, checking if it represents land, which is indicated by the value 1. If it is, we identify all the connected land cells that form an island. This can be achieved by using either depth-first search, DFS, or breadth-first search, BFS, to traverse through all adjacent land cells in 4 possible directions: up, down, left, and right. As we traverse, we mark these cells as visited either by modifying the grid directly, changing 1 to 0, or by maintaining a separate visited matrix. This ensures that each cell in an island is only processed once. In terms of efficiency, the time complexity is O(m*n), because each cell is visited exactly once, where m and n represent the dimensions of the grid. For space, the worst-case requirement is O(m*n), which accounts for the recursion stack in DFS or the queue in BFS when processing large islands. However, the brute force approach has its limitations. There's no optimization to terminate early, and it can be memory-intensive for large grids. To address these issues, we can consider an optimized approach using union find, or disjoint set union. This method reimagines the grid as a graph, where each land cell is treated as a node and edges connect adjacent land cells. The goal is to group connected land cells into distinct components, which represent islands. Using a union find data structure, we can efficiently manage these groups. As we traverse the grid, we perform union operations to link adjacent land cells, and at the end, we count the number of unique root nodes to determine the number of islands. This approach has a time complexity of O(m*n alpha, m*n), where alpha is the nearly constant inverse Ackermann function, thanks to the efficiency of union find operations. It also requires O(m*n) space to store the union find structure. Despite these advantages, it's worth noting that union find is more complex to implement and introduces additional memory overhead compared to DFS or BFS. Given these considerations, the chosen strategy for this problem is the DFS or BFS approach. This method strikes a good balance between simplicity, efficiency, and memory usage. With DFS or BFS, we can explore and mark all cells of an island efficiently, ensuring that each land cell is processed exactly once. This approach aligns well with the core observation that islands are distinct groups of connected components, making DFS and BFS a natural fit for exploring these structures. While UnionFind offers better scalability for extremely large grids, its complexity and additional memory requirements are not necessary for the typical constraints of this problem. It's also worth noting that DFS recursion can lead to stack overflow for very large grids, but this can be mitigated by switching to an iterative BFS implementation, which uses a queue, albeit with slightly increased memory usage. Overall, this approach ensures optimal performance without introducing unnecessary complexity. In conclusion, the DFS or BFS approach is the most practical solution for the number of islands problem. It combines the simplicity of implementation with the efficiency of processing each cell exactly once, making it both effective and easy to understand. This balance of clarity and performance makes it the preferred choice for solving this problem in most real-world scenarios. In this problem, we need to determine the number of islands in a given 2D grid. Each cell in the grid is either 1, representing land, or 0, representing water. An island is formed by connecting adjacent land cells, either horizontally or vertically. The challenge is to count all distinct islands in the grid. To solve this, we can use a brute force approach that leverages depth-first search, or DFS, to traverse and mark connected components. Here's how the algorithm works. First, we define the inputs and outputs. The input is a 2D grid of size n by m, where each cell is either 1 or 0. The output is a single integer, representing the total number of islands. Next, we initialize some variables. We'll use an island_count variable, starting at 0, to keep track of the number of islands we find. Additionally, if the grid cannot be modified, we can use a separate visited matrix to track which cells have already been processed. Once our variables are set up, we iterate over the entire grid using 2 nested loops. For each cell, if it contains 1 and hasn't been visited yet, we increment the island count and perform a depth-first search to explore the entire island connected to that cell. To perform the depth-first search, we define a helper function, DFS, that recursively visits all the cells in the current island. The base case for this function checks if the current cell is out of bounds, is water, or has already been visited. If any of these conditions are true, the function simply returns without doing anything. Otherwise, we mark the current cell as visited. This can be done by setting its value in the grid to 0 or marking it in the visited matrix. Then, we recursively call the DFS function for all adjacent cells, including the ones above, below, to the left, and to the right. Once the DFS traversal is complete for the current island, we return back to the main loop and continue scanning the grid. At the end of the traversal, the island_count variable will hold the total number of distinct islands, which we return as the final result. There are a few key insights to keep in mind for this approach. First, an island is defined as a group of adjacent ones connected in 4 directions, so diagonal connections are not considered. Second, marking cells as visited is crucial to avoid double counting the same island. While directly modifying the grid is space efficient, it won't work if the input is immutable. Lastly, while we use DFS here, BFS is also a viable option, and both methods have the same time complexity. To implement this algorithm, there are a few data structures we rely on. The input grid itself is the primary data structure, as it contains all the information about land and water. If the grid cannot be modified, we can use a visited matrix or a set to keep track of the cells we've already processed. For the traversal, a stack is used for DFS, while a queue would be used for BFS. Now, let's discuss the time and space complexity of this approach. The time complexity is O, n*m, where n is the number of rows and m is the number of columns in the grid. This is because each cell is visited exactly once during the traversal. The space complexity depends on the implementation. If we use a visited matrix, it requires O, n*m, space. Additionally, the recursion stack for DFS can take up to O, n*m, space in the worst case, such as when the entire grid is one large island. To optimize the algorithm, we can modify the grid in place, which eliminates the need for an additional visited matrix and reduces space usage. We can also use an iterative version of DFS or BFS to avoid recursion depth issues, especially in languages with low recursion limits. To illustrate this algorithm, consider the example grid shown here. In the example, we start at the top left cell, which is 0, 0. Since it's a 1, we increment the island count to 1 and begin a depth-first search. During the DFS, we mark 0, 0 as visited, then explore its neighbors. We visit 0, 1, and 1, 0, marking both as visited. Once all connected cells are processed, we finish the DFS for this island. Moving to the next unvisited cell, 0, 2, we see it's a 0, so we skip it. We continue scanning the grid and eventually reach 1, 3, which is a new island. We increment the island count to 2 and perform another DFS. This process continues until all cells in the grid are visited. At the end, we find that there are 3 distinct islands in the grid. This step-by-step approach ensures that every island is counted exactly once, and the algorithm efficiently handles the traversal of all connected components. This Python implementation solves the problem of counting the number of islands in a grid. Let's break down the solution step by step. First, the numberIslands function checks if the grid is empty or invalid. If so, it immediately returns 0 since no islands can exist in an empty grid. Next, we determine the dimensions of the grid, rows and columns, and initialize a counter island_count to track the number of distinct islands. The core of the solution involves a helper function DFS, depth-first search. This function recursively explores the grid to mark all cells that belong to the same island. It takes the current row and column as inputs. If the cell is out of bounds or is water, 0, the function stops further exploration. Otherwise, the cell is marked as visited by setting its value to 0, and the 4 adjacent cells, up, down, left, right, are recursively explored. The outer loops iterate through every cell in the grid. When a land cell, 1, is encountered, it indicates a new island. The island_count is increment, and the DFS function is called to mark all connected cells of this island as visited. Finally, the function returns island_count, which represents the total number of islands in the grid. This solution ensures that every cell is visited once, making the time complexity O, rows asterisk calls, where rows and calls are the grid dimensions. This ensures the solution is efficient and scalable for larger grids. Here, we start with the implementation of the numberIslands method, which takes a 2D grid of characters as input. First, we check if the grid is null or empty. If so, we return 0 since there are no islands to count. Next, we initialize variables for the number of rows and columns in the grid, as well as a counter, islandCount, to keep track of the number of islands we find. Then, we use a nested for loop to iterate through each cell in the grid. If we encounter a cell with the value 1, which represents land, we increment the island count and call our helper method, DFS, to mark all connected land cells as visited. This ensures that we only count each island once. The DFS method is defined below and will handle the depth-first traversal of the grid. In the DFS method, the first step is to check if the current cell is out of bounds or if its value is 0, which indicates either water or a cell that has already been visited. If any of these conditions are met, we simply return. Otherwise, we mark the current cell as visited by setting its value to 0. After that, we recursively call DFS for all 4 adjacent cells, down, up, right, and left, to explore the entire island. This recursive process ensures that all connected land cells are visited and marked, effectively preventing the same island from being counted multiple times. Once the recursion completes, we return to the main method, where the loop continues scanning for any remaining islands in the grid. To solve the number of islands problem, we start by considering a simple 2x2 grid. The input grid contains 1s and 0s, where 1 represents land and 0 represents water. Initially, we set up the grid with island_count equal to 0, and we define a depth-first search, or DFS, function to help us explore connected components of land. The goal of the DFS function is to mark visited cells as 0 to prevent revisiting them. Now, as we iterate through the grid, we encounter a 1 at position 0, 0. This indicates the start of an island. We increment island_count to 1 and call the DFS function at 0, 0. Inside DFS 0, 0, the cell is marked as visited by changing its value to 0. The function then explores its neighbors. Moving downward, DFS 10 marks the cell 10 as visited, and its own neighbors are checked. The cells either go out of bounds or are already visited or water. Similarly, moving to the right, DFS 01 marks 01 as visited and explores its neighbors, which also turn out to be either out of bounds, water, or already visited. This completes the exploration of all connected land for the first island. At this point, any remaining neighbors of 00 are either out of bounds or already visited. The DFS traversal has transformed the grid entirely into water, as all connected ones have been visited and marked as 0. The resulting grid state is a 2x2 grid of all zeros. Since no additional ones remain in the grid, we determine that there is only one island. The output for this example is 1. Next, let's consider a larger grid with multiple islands. The new input grid has 3 rows and 4 columns, with island underscore count initialized to 0. As we start iterating through the grid, the first one is found at position 00. This marks the beginning of the first island. We increment island underscore count to 1 and call the DFS function at 00 to explore all connected land for this island. During the DFS execution for the first island, we mark 00 as visited by changing its value to 0. Exploring its neighbors, DFS 10 marks 10 as visited, but its own neighbors are either water, visited, or out of bounds. Similarly, DFS 01 marks 01 as visited, and its neighbors also turn out to be water or already visited. After finishing the DFS for the first island, the grid state updates to reflect that all connected land for this island has been marked as 0. The updated grid now shows that a new one is present at position 13. This marks the beginning of the second island. We increment island underscore count to 2 and initiate a DFS call at 13. In this traversal, DFS 13 marks 13 as visited and explores its neighbors. Moving downward, DFS 23 marks 23 as visited, and its neighbors are explored. Among them, 22 is another one, so it is marked next. After marking 22 as visited, the remaining neighbors for this island are either water, visited, or out of bounds. At this point, the grid has been fully traversed, and all cells have been marked as 0. The final grid state is entirely water, represented as a grid of all zeros. The total number of islands found in this example is 2, so the output is 2. Finally, consider an edge case where the grid contains only water. In this case, the input is a 2x2 grid of all zeros. Since there are no ones in the grid, no islands are found during the iteration, and island underscore count remains 0. The output for this edge case is 0. The time complexity of this algorithm comes down to how we traverse and explore the grid. First, we iterate over each cell in the grid using nested loops, which gives us a baseline of O, rows asterisk calls, operations, where rows is the number of rows and calls is the number of columns. Now, for every cell that contains a 1, we perform a depth-first search to explore the entire connected component, or island, starting from that cell. During this DFS, every land cell in the island is visited exactly once and marked as 0 to avoid revisiting it. This ensures that no cell is processed more than once. As a result, even with all the DFS calls combined, the total work done by the algorithm remains proportional to the number of cells in the grid. Therefore, the overall time complexity is O, rows asterisk calls, as each cell is visited once either during the initial traversal or as part of a DFS call. The space complexity of this algorithm depends on 2 main factors: the recursion stack used during the DFS, and the storage for the grid. First, let's consider the recursion stack. In the best case, where the grid has sparse islands or no land at all, the depth of recursion is minimal. However, in the worst case, where the entire grid is land, forming one massive island, the recursion stack can grow as deep as the total number of cells, which is O, rows asterisk calls. Now, for the grid itself, we modify it in place by marking visited cells as 0, so no extra memory is required for storing the grid. This means the grid contributes only O1 additional space. Combining these, the overall space complexity is O, rows asterisk calls, in the worst-case scenario due to the recursion stack. When we compare this DFS-based solution to a brute force approach, the efficiency becomes clear. A brute force method would involve examining all possible combinations of cells to determine connectivity, leading to an exponential time complexity of O(2) rows** calls. In contrast, our DFS approach reduces this to O(rows** calls by systematically marking visited cells and using recursive exploration. Let's also break this down into different cases. In the best case, where all cells are water, 0, no DFS calls are made, and the complexity is O(rows** calls for grid traversal alone. In the average case, with a mix of zeros and ones, the complexity remains O(rows** calls, because the number of DFS calls and recursion depth are proportional to the number of ones. Finally, in the worst case, where the grid is entirely land, forming a single massive island, both the time and space complexities are O(rows** calls, due to the exhaustive DFS exploration and recursion stack depth. To mathematically justify the time complexity of O(rows** calls, consider this: each cell in the grid is visited at most once. During traversal, we check each cell individually, and when a DFS is triggered, we explore all reachable cells in the corresponding island. However, since visited cells are marked as 0, they are never revisited. As a result, the total number of operations is directly proportional to the total number of cells, which is rows multiplied by COLS. For space complexity, the depth of the recursion stack determines the additional memory usage. This depth is bounded by the size of the largest island, which in the worst case is O(rows** calls. Since the grid is modified in place, no extra storage is required beyond the recursion stack. Therefore, the space complexity is also O(rows** calls in the worst case scenario. One of the most common mistakes when solving the number of islands problem is not marking cells as visited immediately during traversal. This can be a critical issue because if you delay marking a cell, you might revisit it later, which could either lead to infinite loops in a depth-first search or inaccurate results in a breadth-first search. To avoid this, you should mark a cell as visited as soon as it is processed. This can be done by modifying the grid directly or by maintaining a separate visited array. Another frequent error involves mishandling boundary conditions during grid traversal. For instance, not checking whether indices go out of bounds, such as I0 or j equals n, can lead to runtime errors. Always ensure boundary checks are in place before accessing grid cells. Additionally, on coding platforms, it's easy to forget to reset the state between test cases. If you're using global variables like a visited array, failing to reinitialize them can introduce carryover state, which will produce incorrect results. To prevent this, reinitialize all necessary data structures at the start of each test case to ensure a clean slate every time. Another pitfall is inefficient island marking in DFS. If you repeatedly traverse cells that have already been visited, you're unnecessarily increasing time complexity. A better approach is to optimize your recursion by leveraging the visited state effectively to minimize redundant checks. Another issue arises when using iterative DFS without managing the stack size. For example, in large grids, the stack can grow excessively, leading to stack overflow errors. In such cases, it's often better to use a queue-based BFS for an iterative solution, as it avoids stack limitations. Alternatively, if you're committed to DFS, you might need to adjust recursion depth limits to handle larger grids. On the interview side, it's important to recognize that many grid-based problems share similar traversal techniques, like DFS and BFS. Mastering these will help with related challenges like flood fill or connected components. Remember that interviewers often test edge cases such as 1x1 grids, empty grids, or grids without any land or water, so it's crucial to account for these in your solution. If you want to stand out, you can also discuss less common optimizations, like using union find for connected components. Finally, communication is key. Clearly explain your choice between DFS and BFS, and highlight the trade-offs, such as simplicity versus memory efficiency. The number of islands problem has many related problems that you might encounter. For instance, LeetCode 695 asks you to find the maximum area of an island, while LeetCode 463 focuses on calculating the perimeter of an island. Another interesting variation is LeetCode 130, which deals with surrounded regions. These problems all build on similar concepts, so the skills you develop here will transfer well. When it comes to alternative approaches, union find, or disjoint set union, is a powerful technique for finding connected components. While it is highly efficient in static grids, it does come with a steeper learning curve and more complex implementation. This makes it ideal for scenarios where you need to pre-process connected components. Another option is iterative BFS. This method avoids issues with Stack Overflow, making it more memory efficient than recursive DFS. However, managing the queue can sometimes introduce overhead, so it's a trade-off to consider. This approach is particularly useful for solving problems on large grids where recursion depth is a limitation. Finally, recursive DFS remains one of the simplest and most intuitive methods for solving the number of islands problem. It is easy to implement and often the go-to choice for smaller grids, where Stack Overflow is not a concern. However, it does have limitations. On larger grids, the recursion depth may exceed the system's limits, leading to Stack Overflow errors. For cases where simplicity is more important than scalability, recursive DFS is an excellent choice. By understanding the trade-offs between these techniques, you can select the most appropriate method for the problem at hand and demonstrate both your technical skills and your ability to make informed decisions. Great job! To recap, we solved the number of islands problem using graph traversal techniques like DFS and BFS, with a time complexity of O(m*n). Remember the importance of connected components and grid traversal for similar challenges. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!